For our fifth and final video from Bruice chapter 16 here for organic, we're going to expand our synthetic toolbox a little bit and then look at unsaturated aldehydes, ketones, and derivatives when we've got a double bond to think about as well. Okay, but first, let's expand our synthetic toolbox a little bit. Look at designing a synthesis. A couple of key words here from 16.14. Disconnections, synthons, and synthetic equivalents. Okay, what are these all about? Because as we have more and more reactions, more and more functional groups, right, these designing a synthesis gets harder and harder. So let's try and simplify that a little bit, right? Keeping in mind that synthetic routes can be challenging. They're not always easy to design, which is why from the beginning, we've learned that process of working backward, right? Doing a retrosynthesis or a retrosynthetic analysis. And one useful step when you're doing that is something that's called a disconnection. Choose a bond somewhere in the molecule, break it, and make two new fragments. Those fragments are called synthons. And a key thing is that your synthons don't have to be real molecules, right? They're just something that's kind of spurring your mind and getting you to think about something else. When you're breaking a bond, you're just putting the electrons one way, right? You're breaking it heterolytically, not homolytically. So something's going to end up being positively charged, something else negatively. We don't want two radicals when we break it. So chances are it's not a real molecule, but then you're thinking about other groups that might get it to behave like that. So you're using a synthon, which is a made-up molecule, to discover something that's more real, right? That's called a synthetic equivalent. And a synthetic equivalent is a reagent that's actually used as the source of the synthon. Right? So the overall retrosynthesis, right? What you're trying to make, you work backward, however many steps you need to get to the original starting material. So what does that look like here, right? If we're trying to do a retrosynthesis here of phenol, I do a disconnection along this bond, right? Produce two synthons here with a carbocation, here as hydride. And then I think, okay, well, what could be equivalent to those? Well, hydride, I know I can get from a reducing agent, sodium borohydride in this case, and a positively charged next to that alcohol group, well, carbon with a positive charge, right? I see that on a carbonyl here. And then that kind of spurs my memory. All right, I know I can take a ketone with a reducing agent, right? Reduce it to an alkoxide, then acid will turn it into an alcohol. But you have to be careful in this process, choosing where you're going to disconnect these bonds and break them up. And then after you break it, where to put the charge. Because, you know, what if I did a different type of disconnection? Instead of breaking the CH bond, I tried to break the COH bond. Okay, keeping in mind the CH is still floating around back here, not shown. Right? I do a disconnection, then I put a positive charge on cyclohexane, and I have hydroxide as well. I could get both of these in theory, right? Hydroxide, I can get a source of that just in a basic solution, and I can get a positive charge on carbon, right? Not a full positive, but a partial positive by putting a halogen on there. But if I do that as my synthetic route, right, I'm going to get a lower overall yield because I've got competing reactions. I've got a substitution reaction, but also an elimination reaction. Remember those from chapter 9 and 10. So because I'm getting two products here, although one of them is one that I want, I'm getting a lower overall yield. And so that's not a great choice. So that's an example of choosing a bond to break, but what about where to put the charges? And chances are this is just going to be trial and error, right? Try it a couple different ways until you figure out something that's good, that works. Because if I do it a different way, right, now I put a positive charge on my phenol here. So now I've broken this C bond, right? Cut off the methyl group. Right? Well, I put a positive charge here. I'm looking for a minus CH3. Okay, it's kind of a carbanion source. And you can do that, right? This would be an okay route to go. We haven't covered chapter 11 yet, but you can get this carbanion source from this guy, number 1. It's known as a Grignard reagent. I will cover those soon. Right? But breaking a different bond down here, right? breaking that CC bond. We've mentioned it several times throughout Organic 1 and Organic 2. Carbon-carbon bonds are not incredibly easy to form, right? So I wouldn't do a disconnection over here or a disconnection down here or anything to interrupt my cyclohexane, because it's going to be extremely difficult to reform that, right? I can't easily think of a synthetic equivalent coming from those synthons. So be careful. Choose a wise bond to break, and then put the positive charge and the negative charge in the appropriate places so that you can lead yourself to the synthetic equivalents. And one more note, I'm jumping back a slide again here. Actually, I'm going to go back one more, right? Keep in mind, right, this is a synthon, and you're just using it to discover you need some sort of synthetic equivalent down here that's got not a full positive charge, but a partial positive charge. So it's kind of a guideline to discover what the electrophile and the nucleophile are going to be acting as in your solution, right? Same thing. This synthon has a positive charge here. We know that that carbon needs a partial positive charge, okay? Because we couldn't have full positive and full negative charges floating around. Okay. So that brings us to 16.15, talking about alpha beta unsaturated aldehydes and ketones. Okay. And a couple more considerations in terms of reactivity. Okay. Because if I've got something that's alpha beta unsaturated, keeping in mind my carbonyl isn't counted in the letter nomenclature, right? So it's alpha carbon, then beta carbon. Right. If I've got something that's alpha beta unsaturated, meaning there's a double bond between the alpha carbon and the beta carbon, right? Now I've got two possible electrophilic sites, right? I've got my traditional electrophilic site over here on this carbon that we've been talking about for 2 chapters. But if I think about the resonance contributors, this carbon, the beta carbon, is also a possible electrophilic site. And we're going to talk about both of those and which one we react with. Think about the carbonyl first. Looking at my carbonyl, if I just have a nucleophile come in and directly attack that carbon, as I have been doing, that's known as a direct addition. Also known as a 1,2 addition, keeping the oxygen as number 1, that's carbon 2. A 1,2 addition, more commonly known as a direct addition. If we have a direct addition, that's the same as everything we've been thinking about before, right? Nucleophile adds, we protonate to get a neutral product, we're done. Nothing new. But if I go to that other beta carbon, that's known as a conjugate addition, okay, or a 1,4 addition. Now we're 1, 2, 3, 4. So a conjugate addition, also known as a 1,4 addition, that's where I'm adding to the beta carbon. And how does that work out? Okay. First step is my nucleophile comes in and attacks the beta carbon. Then my pi bond shifts over to between carbon 2 and carbon 3. And to avoid getting a Texas carbon here on C2, my pi density in the CO bond comes back up to oxygen. And the initial product of a conjugate addition to an unsaturated aldehyde or ketone is an enol. Remember from chapter 7, we discussed an enol, right? En from the alkene, ol from the alcohol. So this is an enol over here. And back in chapter 7, we learned a keto-enol tautomerization, right? So my enol tautomerizes to the keto tautomer. That's something that we covered before. Right? So now the question is, right, and at the end of the day, we've just added the nucleophile, right, to the beta carbon, and we've added a hydrogen to the alpha carbon. But now the question is, right, which one do we do? Because we just saw that they're both possible, a direct addition or a conjugate addition. And what controls that is both the identity of the nucleophile, specifically its basicity, and the structure of your alpha beta unsaturated aldehyde or ketone. So let's revisit thermodynamic control from earlier in the semester. Now, if I've got competing reactions, okay, and I've got something that's reversible here, I'm going to be under thermodynamic control, meaning this one can keep bouncing back and forth, but when I fall down here, I stop. If something's under thermodynamic control, your major product is the more stable product. And the more stable product, if you're thinking about direct or conjugate addition, is always coming from the conjugate addition. Say that differently, the conjugate product is the major product when you're under thermodynamic control because you've maintained the carbonyl from start to finish, which is inherently stable. Okay. So we need to look at our nucleophile. If our nucleophile is weakly basic, okay, so our nucleophile is a weak base, that means that the direct addition is reversible. Here, notice the equilibrium arrow, right? Because I can bring electron density and kick that back off because it's an okay leaving group. Right? So weakly basic nucleophile means we're under thermodynamic control, meaning the conjugate product, right, from the 1,4, the conjugate addition, is the major product. Okay? So if our nucleophile that's in the middle here is a halide, right, cyanide, a thiol, an alcohol, or an amine, any of those are weakly basic, right? Conjugate addition will prevail. But what if I have a strong base, right? So something like hydride or a Grignard reagent, and I'm getting just slightly ahead of myself in the slides, right? So here we see a whole bunch of weak bases, kinetic, we're under thermodynamic control still, weak base, thermodynamic control, everything here on slide 114 is showing that. Okay? So there's a weak base, conjugate product prevails, the 1,4 addition. Okay? And I would recommend writing this down, right? Weak bases form conjugate addition products. That's what we've been saying before I started to get ahead of myself, which now I can do on slide 115, where we go to kinetic control, where I have a strong base. And so the opposite of that is strong bases form direct addition products. Okay? So here I have a strong base, right? Something like hydride, and it can go either way. And it's not to say that we only form the direct product, right? If you've got a strong base as your nucleophile, it could be direct, it could be conjugate, right? It just depends on the reactivity of your carbonyl, right? Because both of these now, there's no equilibrium arrow, both are irreversible. So whichever one of these guys is formed faster is going to be the major product because I'm now under kinetic control, just whoever gets formed faster because I can't go back. So I need to think about the reactivity of my carbonyl. Okay? Now, aldehydes, right, are not super sterically hindered. They, by definition, have to have a hydrogen coming off one side of the carbonyl. So an aldehyde plus a strong base, these are both strong bases, right? A hydride source and a Grignard, strong bases. So aldehyde, strong base, that'll favor the direct addition. Okay. But as we increase the steric hindrance, we get more and more conjugate addition, right? Going from a ketone to then a sterically hindered ketone, right? Notice in this situation, I've got a ketone, I've got some steric hindrance on both sides. This favors the conjugate addition. I've added to the beta carbon over here. Now notice I've got two possible sites to be alpha beta unsaturated. Here I've got a pi bond between alpha carbon and beta carbon. Over here, pi bond between alpha carbon and beta carbon. But that should make sense. I'm not going to mess up that pi bond in benzene, right? Because I would be interrupting the inherent aromaticity over here. Now, again, if my carbonyl doesn't have a ton of steric hindrance, now I'm thinking about a ketone, it's got some, but not a ton, then I've got two competing reactions. And notice in this situation, I get a mix of the direct product and the conjugate product. So to summarize that overall, right, your conjugate addition is generally irreversible, favored by sterics. We're under kinetic control. The direct addition can be reversible or irreversible. So pay attention to the nucleophile, pay attention to the sterics of the aldehyde or the ketone to determine your product. Last consideration from this chapter is alpha beta unsaturated carboxylic acid derivatives. Okay, what are these guys going to do? So our derivatives from chapter 15 plus they're unsaturated in the alpha beta position. These guys, again, it depends we could do both. We can do a nucleophilic acyl substitution, right? These won't do a direct addition because they have leaving groups, but they can do a nucleophilic acyl substitution, or they could do a conjugate addition. And it just depends on the leaving group, right? If I have a good leaving group, my more reactive derivatives, those will still continue to do nucleophilic acyl substitution. But if I have bad leaving groups, okay, then I will just continue to do conjugate additions. And that's an important thing that goes on in our bodies, right, with some of the isomerases, those enzymes in your bodies, as well as in the synthesis of glucose, which the textbook discusses further. So summary from this video: know synthetic equivalents, synthons, and disconnections, and know the reactivity of alpha, beta, unsaturated aldehydes, ketones, and derivatives. Do they do a direct addition? Do they do a conjugate addition? Or do we see a mix of both? And that concludes chapter 16.